And somebody in the back is waving, looking for help. There we go. Um, all right. Uh, so we're, I think, about at time to get things rolling. So we'll get things rolling. The session is recording as usual. I'm recording the screen without the faces and things of that sort. So uh, I'm recording this screen, and hopefully you can see the presenting of the lesson plan and all that stuff. So when we're done, I'll put the link for the recording here. Um, Today we're going to go through and just take a little bit of a look at the lab that we were supposed to be working on Friday. I think I set the due date uh, as this morning or maybe yesterday. I forget what I did for the due date. So we'll go through, we'll take a look at this lab, the relationship between current and electric potential difference. Um, Make sure that thing has a reasonable sense. And then we'll make sure that we understand the graph, the trend line, and the equation for that stuff there. Um, so and then the rest of the assignment is there's a Google form posted that again goes through the lab from last week, or all the activities from last week, just to try to make sure we've got some sense made out of it. So the Pivot Interactives lab, we're supposed to kind of set up a circuit that looks something like this, and go through and collect some data and get some things lined up. Um, there are questions through here. Um, the things I want to focus on when we look at the setup of things, and the data collection, collect your data and make a graph. If you see something like this, remember these little arrow thingies drop information down, and you'll see here, it looks like if you look really quickly, it looks like there's maybe nothing in here. I click this. When I click data collection and graphing tips, when I click that, it says, hey, please complete and submit the previous section. If you don't read that, you might miss that it's actually telling you to do something first. So we have to click this lock answer and continue. That's just saying, hey, make sure you did actually do this stuff first. So hit that. And now we see this data collection and graphing tips show up. There were a few people that forgot or didn't see that little drop, that the need to hit the lockdown, and missed a section. So experiment one, planning. There are just some notes here. Resistance is how much an item opposes or resists current flow. And this talks about our setup. The thing that we're going to try to keep constant is the resistance. We're not going to change the resistance of the bulb. Um, and the thing that we're going to change directly was the potential difference of the battery. We have the slider there that allows us to adjust the potential difference of the battery. And the dependent variable, the thing that changes because we change the potential difference of the battery, is the current. Um, but then we have to hit this lock answer and continue spot. Lock answer, continue. Now you see these spots for the data table show up. Um, and I had data collected in here and I forgot to, oops, keep that in there. Um, so we should have data that looks something like that. There are kind of two variations to it. So if we have data that looks something like that, then we go over here and we hit curve fits. And then we can say proportional or linear. If I go with linear, floop, the line straight through there. And we've got this information for the equation down here. Um, who's buying cookies? uh, we'll try to get Kathleen to. Hey, if anybody's in the room with Kathleen, can you ask her to mute her microphone? That would be delightful. Um, there we go. Thanks, guys. Um, hard to disrupt an entrepreneur in the making there. 1,000 boxes? That's a boatload of boxes of cookies. Um, so when we're looking at this stuff, this tells us the relationship that we get down here. One thing I want to show you that has caused some confusion, I think, for a few people when they're analyzing this. Let's say I have something here when I'm collecting it, and let's say my numbers are off just a little bit for whatever reason, which is perfectly reasonable and acceptable. The issue I want to point out is um, like this number now is not zero, but it's pretty close to zero for the b, for the y-intercept. If I change this and make it, we'll make it even smaller difference, then we see this number is getting even smaller still, right? For b, for the y-intercept. It's not zero, but it's pretty stinking close to zero. So that's not a huge deal. And as this gets smaller and smaller, um, what ends up happening is at some point this switches to scientific notation, and instead of putting all of these zeros in, it changes it um, to something that looks a bit different. And now we see this number that I wanted to kind of point out. That looks a little bit different. They say the y-intercept b is -2e, -9. That's like it's like scientific notation, which you might have done for a minute in middle school. So instead of being 2, this is like 2 times 10 to the -9th, all your exponents. It basically means it's -2 divided by 10 9 times. So it's actually 0 point and then 0.000000002. So that's actually a really small number, very close to zero. So I neglected to or forgot to bring up again this bit of scientific notation um, when you started doing this. So the reason I point that out is that as we go on to some of these other questions and in the analysis section, when it asks you, oh, I guess it wasn't in the analysis, it was in the interpret your graph section. When it asks you to analyze things and it talks about what you would expect your y-intercept to be and what your y-intercept actually was, um, that's a spot where we need to be able to understand what this part is. And this is really 0.000000002, which is a pretty darn small number, and we could probably say close enough to zero to think of it as being essentially zero. So I wanted to make sure we had that taken care of. And then this question causes concern, and it's I have a really difficult time uh, commenting on this or writing this down as text sometimes. So what I'm trying to get at is what the y-intercept represents and how that makes sense. So the y-intercept for all graphs is the value of whatever's plotted on y when the x-axis is zero. And in this graph, the thing that's plotted on the y-axis is actually current. So we should be saying that's current. So the y-intercept represents the current when the And then this is whatever's plotted on the x-axis, which is the potential difference. So when the potential difference is 0, what should the current be? And when the potential difference or the voltage is 0, the current should be 0. Our y-intercept should be 0, right? If the battery is completely dead, or if there is no battery, it's really tough to make a light bulb light, or at least you need to find some other way to provide a potential difference. So we would expect that when the potential difference is 0, that the current would be 0. We would expect our y-intercept to be 0. Um, and then from there, the big parts that I wanted to get to are the relationship that we get. And some people got to the summary, clicked the drop down, and didn't see stuff. Yeah, that's again, make sure you read the statements, right? Please complete and submit the previous section before continuing to this one. We have to hit lock answer and continue. So then there's a summary and like 2 questions. So the summary that I want to look at, this is the big part here, right? From this relationship, we had on the y-axis, we had current. On the x-axis, we had the potential difference. And then it turns out that the slope, if we look maybe at this one, and it turns out that I'll take a look at that again. The y-axis was current. The x-axis was potential difference or voltage across the light bulb. And it turns out that the slope should be 1 over the resistance. So this equation of I, or current, is 1 over the resistance times the potential difference. This equation can be written like this, or it can be written like this. Current is the potential difference divided by resistance. This equation is really useful when people are trying to figure out different ways to make circuits work. It's often called Ohm's law, after one of the people that first discovered this. So that relationship is one of the big takeaways from this lab. So this lab is trying to collect data to plot things out, to see that this relationship is how things work. And remember that that's how like all physics works, right? They Scientists, physicists would collect data, plot things out, see what they get, and hey, that whatever you get from the equation is how things work. And so they're not making things up to come up with these equations. They're not saying, I bet it feels something like this. That's not what happens, right? We collect data, plot it out. What the graph tells us is the way the world behaves. So that's where that stuff comes from. Then let's see. Then this is looking on to the stuff from the assignment posted today. So I just wanted to review a couple of things here. We're about halfway through class, and I think we're halfway through the time allotted to us, and I think probably more than that through what I plan to go through today. So we'll finish probably before 11. Fine by me. I'm sure it's fine by you. Just giving you the heads up there. So reviewing terms, remember electric potential is talking about the energy per charge. That becomes really useful when we start looking at things like the loop rule and the junction rule and stuff like that. Electric potential is the energy per charge. So if you think about all those little blue electrons in that simulation moving around the loop, electric potential is the energy per blue electron in that simulation. Now, electrons aren't necessarily blue, and there's not just one of them moving, but for a simulation trying to visualize some things, that's useful. And then current is often thought of as how fast electrons go, but that's not exactly right. It's not just how fast they go. Excuse me. The current is kind of how many charges pass by a spot per second. So it could be like, hey, there's just a few moving, but they're moving really fast, so there's a lot going by per second. But current can also mean that instead of just one going by really fast, it could mean that there's a bunch of them going by. and maybe not fast, maybe they're moving fairly slow, but there's a bunch moving by. So current is kind of how many charges are going past a point per second. And that's so it's like charges per second. And then resistance is how much an item opposes or resists the flow of electricity. So we usually talk about things like a wire or the filament in a light bulb or a resistor or like speakers, how much resistance is present in those devices. And then this is a couple of different ways to summarize what we just did with that Pivot Interactives lab. One way to talk about what we get with this is that if the potential difference increases, the current should increase. This funky little almost a fish symbol thingy in between is read as proportional to. So the current in the bulb is proportional to the potential difference across the bulb. If the potential difference doubles, the current doubles. If the potential difference triples, the current triples. If we reduce the potential difference to half the original value, then the current should also reduce to half of its value. So whatever happens to one, the exact same thing happens to the other. Now, that doesn't mean that they're the same value. It doesn't mean that the current is 3 and the potential difference is 3. It just means if one doubles, the other doubles. And then the other part of that relationship is that the current in the bulb is also proportional to 1 over the resistance of that bulb or the resistor or the speaker or whatever electrical device we're looking at. So if the resistance is 1, well, 1 over 1, we'd get a current of 1. If I double the resistance, and instead of the resistance being 1, we now say the resistance is 2. Well, 1 over 2 is 0.5. So the resistance doubled from 1 to 2. And that means this would reduce to half of what it was. 1 divided by 2 is 0.5. So this is the way of saying that if the resistance gets bigger, the current gets smaller. So if the resistance goes up, current goes down. And putting all that stuff together is this Ohm's law relationship again. Current is potential difference over resistance. And I forgot, I was going to open up this little ditty here. This is just a nice visual for the relationship. While that's loading, we'll go back here. Oops, not there. There. So when we're looking at this equation, this is a really common way to state Ohm's law. We can also rearrange and solve for get R by itself or get potential difference by itself. And the simulation has potential difference by itself on one side. So with the simulation, we'll look at there. So this is still Ohm's law, but instead of I on one side and V and R on the other, they put V on one side and IR on the other. So this is still Ohm's law, just rearranged and solved for something else. And this isn't going to be a life-changing simulation, but it's kind of a nice representation. So if we look at the I, if you look at the current, right now the potential difference is 4.5. So that's like the potential difference motivating charges to go through this device, through this resistor. If I take the 4.5 and I double it to like 9, well, then the current doubled and this I got bigger. If I take the resistance and drop it from 500 ohms down to 250, right? So stop and think. If the current right now is 18 and I drop the resistance down to half the value, what should the current become? So you can stop and think that for your second. I don't know if I can type numbers in. I can't. So, and it won't let me use my arrow keys. So it'd be about 36 if I were able to actually get that at 250 on the dot there, right? So the simulation does a nice job of just kind of showing us how if one thing gets bigger, the other, what happens with the others. You're missing the sound, I think. I'm hearing it in my earpiece. So I share that with you. All right. So this simulation is just a nice little bit to kind of show us how this stuff all goes together. And you see that if the voltage increases, it adds batteries, or if the potential difference increases, it's adding batteries. Um, they don't really do much to show the. I guess they show a little bit of like there are more obstacles in the material here if the resistance increases, and fewer obstacles if the resistance decreases. Um, so we've got that bugger done. Um, and I think we're pretty much at the spot where we've reviewed just about everything. Um, oh, I didn't show you this. Just as a reminder, remember there's a voltmeter. If we're going to measure the potential difference of a resistor, we draw a voltmeter across it like that. This checks the voltage or the electric potential on one side of the item and on the other side of the item. So whatever this reads is the potential difference across this resistor. Some folks would say it's the drop in potential across the resistor. It's really a variety of ways to say that that item uses 3.3 volts or takes that much energy from charges. And if everything is in a series or in a loop, a single loop, then the current everywhere is the same. So we've got something like that. Um, Let's see. Oh, there was one more thing I forgot. My apologies. I'm going to go back here, not to do this as the lab, but just because I have that open up on top. So the last thing I wanted to show. Um, let's see. I'm going to shrink things down here like this. Zoop, zoop. um, and we'll go, I'm just going to add one more branch, one more path. So if I add another path in parallel to show circuit stuff happening, if we go like this, and like that, and like that, so now we have the current has the opportunity to split, right? So at this junction right here, some of these blue electrons go up to the light bulb on top. Some of them just go straight to the left through this light bulb here. We see that there's zero 0.9 amps here and 0.9 amps here. But remember, when we talk about current, that's charges per second. So not all charges are going down this path. Some charges are going down this path. Other charges are going along this path. So if I put an ammeter right there, right next to the battery, think for a second, what should the current be uh, flowing through the battery? If this one was 0.9 and this one was 0.9, what should the current here be? 1.8. Yeah. So what we're saying is all of the flow goes through the battery, all of the flow goes through this wire and this wire, and then some goes up and some goes over. If I change this bulb, right now both bulbs are identical. They both have 10 ohms of resistance. So if I change this bulb and I change the resistance of this bulb, we'll see that all of our, well, most of our numbers changed. If I change the resistance of this bulb, there's less current going through here, right? So we saw with Ohm's law, if the resistance changes, the current should change. So the resistance changed and our current changed. Up here, we did not change the resistance of this one. The current didn't change. It's on a different path. So the current on a path stays the same, but on different paths, not necessarily changing. So this path with that wire, this bulb, this wire, the ammeter, this is all one path with no splits in the path. Before the path, yes. After the path, yes. But within this path, there are no splits. So the current everywhere here is the same. And then here, 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 here. That again is a path that doesn't have any splits within it. So the current here is 0.9, the current through this bulb is 0.9, and we see down here, the current again is still the total, 1.06 charges per second going through here, and then some split there and some split here. So That's that junction rule or that current junction rule. The total charge into a junction equals the total charge out. So if the total charge per second here is 1.06, so at this point, if there's 1.06 charges per second coming in, there has to be 1.06 charges per second going out. In this example, 1.06 coming in, 0.9 going up, 0.16 going to the left. That's that junction rule. When we look at the loop rule, and it's easier if I can draw on the screen, but this won't pick things up. When we look at the loop rule, we can say that the total potential around a loop is 0. So if the battery gives us 9 volts of potential, 9 volts of potential there, uses 0, uses 0, uses 0, uses 0. This bulb should use 9 volts and then back to the battery. So there's just one loop there. We're getting really close to the end of the period here. I'm going to see if I can get this sketched in to another screen. Try and paste this into a doc real quick because the drawing is often helpful. Oh, shoot, I hit the wrong button. Well, that's going to probably take the time I had. Copy there. Here, we'll go down here. So if we put this stuff in, paste, turn this thing off because that's annoying. So now if we're going to start to take a look at this, drawing tools are always different. Copy, insert, drawing, new, paste that bugger in. Come on now, get in there. So now if we're looking at this part and we're going to try to take a look at the loops, we have 2 different loops. We have this loop where the total in this loop would be 0. We have plus 9 here and minus 9 here. So it'd be plus 9 for the battery, minus 9 for this bulb. And then if we go to a different loop, the outer loop, we'd have from here through here, all the way up to the top, and then down. And for that loop, you would have, we'd have again, plus 9 for the battery, 0, 0, 0, 0, 0. And then this bulb would use the 9 volts and back to 0 again. So plus 9, minus 9, back to 0 for that loop rule. That loop rule where we can talk about delta V for the battery compared to delta V for the other parts of the circuit. Stuff like this. Yeah, time's at the end. So you guys got to go. Have a good one. I'll post this recording into the lesson plan, and there you go. Have a good one, folks. So just the summary, loop rule. And I have to go as well. Let me know if you have any questions. You can email or do what you need to do.